Okay, question 7 asks about the 3 ways that a limit might fail to exist. I'm going to use this one picture here to show 2 of them. For example, one way that a limit could fail to exist, it happens here at x equals 2. If I were to walk along this function, coming toward the place where x equals 2, if I came from the left direction, I'm approaching that y value there, which looks like y equals 2. If I were to approach instead from the right-hand side, my function approaches that value, which looks like y equals 1. I have a different limit from the left as I do from the right. This is one case where the limit might fail to exist. A second way the limit might fail to exist is if, as I approach a certain x value, for example, x equals -1, what if I'm approaching and my y values here, they start to get bigger and bigger and bigger and bigger and bigger. And if this comes all the way up toward infinity, because, for example, x equals -1 is an asymptote, a vertical asymptote, then my y value could get as big as infinity. Well, infinity is limitless, so there is no limit. If my function approaches, if the y value approaches positive infinity or negative infinity, as I let the function approach that particular x value. The third way that a limit could fail to exist has to do with oscillating functions. Won't come up for us in calculus AB or BC, and it's really hard to draw. So if you can find an example and draw it in on your paper, I'll give you extra credit. So just a quick note here, I've got this picture up. The limit of a function has to do with the y value the function approaches, and actually has nothing at all to do with the actual y value of the function at that place. So for example, this picture that I have here, the limit as x approaches 2 of f of x has to do with the y value up there, which I'm approaching from both sides, has nothing to do with the actual y value when x is 2, which is 1. So here the limit of f of x as x approaches 2 is 2, not 1. So here we have an example of what we talked about just a minute ago. This limit, the limit of this function, let me get my whiteboard up, of this function as x approaches c doesn't exist, because as I approach x equals c from one direction, I'm headed for one y value, and as I approach x equals c from the other direction, I'm headed for a different y value. So here the limit fails to exist at x equals c. But I still might want to talk about this. So we need to know a notation. We have a notation so we can write about the limit of a function as I approach from one direction, without having to worry about what happens when I approach from the other direction. So you'll want to write in this notation for a one-sided limit. I'm looking here, you see a place to write this in your notes. We say the limit of f of x as x approaches c from the right equals L. It's this little plus sign down here that tells us we want to approach only from the right. So this example matches. As x approaches c from the right, so I'm going to come from the right-hand direction. What's the y value I'm approaching? It's L. Similarly, down here, the limit of f of x as x approaches c from the left, with a little minus sign up top, in this case equals k. So make sure you write that notation in. So now that we know this notation for limit from the left-hand side and limit from the right-hand side, we can formalize our definition of what it means for a function to have a limit at a certain x value. So here, a function f of x has a limit as x approaches c, some particular x value, and that limit, we're going to call it L. That's only true, that function f only has a limit if the limit of the function f of x as x approaches c from the right-hand side is equal to the limit as x approaches c from the left-hand side of the function. So you can write those words into your paper, and you see there's also a place for you to write this theorem, theorem 3, in symbols.